get to start it. All right, so now we're going to go on to chapter 18. It's called the reactions of aromatic compounds. All right, so we're going to look at one basic type of reaction for benzene. Okay, and they are called electrophilic aromatic substitution reactions. Okay, we're going to be able to add various groups, but they're all going to follow the same type of mechanism. Okay? So here's the learning objectives for this. We're going to look at kind of the generic mechanism first, and then we're going to learn how to add, I think it's 5 different groups. Okay? Once we've done that, we're going to take a little break. I'm going to do this slightly out of order of what the text has. We're going to look at how we can modify those substituents once we put them on. Okay? Then we're going to come back and we're going to look at what would happen if we put a second group on, or a third group. And it turns out that when we have a substituent on the ring, that's going to influence how the second reaction takes place. All right? So we already mentioned, but it was more or less kind of in just talking or text. We didn't write it out. The difference in reactivity between an alkene and benzene, right? So we know, or we should know, right, that if we react an alkene like this, like cyclohexene, with bromine, right, then it should do a electrophilic addition reaction. And we get 2 bromines added, and they are anti to one another. Remember, it comes in from the one side, forms a bromonium ion, and the bromide comes in and opens up that bromonium ion ring. When we do this with a benzene ring, like I said before, essentially this gives no reaction. Okay? However, if we add bromine and we add a catalyst, in this case what we're going to do is we're going to add this iron tribromide. It's going to act as a catalyst. It functions as a, oops, my W was upside down for some reason, a Lewis acid. All right, and if we do this, oops, and I should have 2 there, then we don't do the addition reaction, but we get a substitution reaction. All right, so we could have plus HBr. Okay, so up here on the top, this was an electrophilic addition. This one down here is also electrophilic, but it's called an aromatic substitution. All right, so the electrophilic part tells us that the reaction is going to essentially at least begin in the same way. All right, so when we had an electrophilic addition reaction, what role did the alkene play? What did it function as? A nucleophile, right? So the electrophilic part is that the alkene was reacting with an electrophile, so it was behaving as a nucleophile. Okay? Same thing with benzene. Benzene is going to act as a nucleophile. It's going to react with an electrophile. All right, so let's the generic kind of sequence here. So I just have this E plus. This is just going to be our electrophile. And when we look at various reactions in this chapter, they're just going to differ in what that electrophile is. Okay? So like with just alkenes, the first step is going to be one of the pi bonds, and this is partly why we draw out distinct pi bonds instead of just a circle, because it's easier to keep track of the electrons. We're going to have this pi bond come over and react with the electrophile. Okay, and one thing that makes this easier, I would do this in the beginning at least, is whichever those pi bonds you're choosing to show the reaction to, draw the hydrogens there, just so you don't forget about them. Okay? So if we do that, okay, that E group is going to attach to one of those carbons. We're going to get something like this. These other two double bonds so far have been unaffected. And what else needs to go where that hydrogen is? A positive charge. Right? So just like with the electrophilic addition reactions of alkenes, we formed a carbocation as an intermediate. Now, this carbocation is kind of special compared to normal carbocations in that it has lots of resonance. Okay, so it's going to be a resonance stabilized carbocation. We can draw the resonance if we just look at this. We can think about the kind of the generic situations for resonance. Here we have an atom with a plus charge on it next to a pi bond. All right, so we can push this pi bond towards the plus, and we can draw another resonance structure here. Puts the plus over on this other side. All right, then if we look at this again, we have another pi bond next to this cation, so we can do the same thing again. And we can generate another resonance structure like this. Okay, so that plus charge is actually spread over 3 different carbons. Okay, so that stabilizes this carbocation. So we could just call this a resonance stabilized carbocation. All right, so if this was doing just a electrophilic addition reaction, then we would have some nucleophile that would react with the carbocation, right? And it could, in theory, react at either of 3 positions to, in this case, give 2 different products, right? However, because benzene is so stable, if we did an addition reaction, let's do it like this. If we did an addition, and I'll just, how do I want to do this? I'm going to just draw a nucleophile. Let's put a minus on it. If this were going to react with that carbocation, we would get something like this. This would have an H on it too, and our nucleophile. Okay, so this would be an addition product. Okay, so now let's look at what's going to happen if we actually do the substitution. So in this case, I'm going to draw it not as a nucleophile, but as a base. Right? We know that nucleophiles and bases can do the same kinds of things. They're both using a pair of electrons to donate electrons. So in this case, what happens is this base reacts with the proton that's on the same carbon as the electrophile. Okay? Because that's the sp3 hybridized center right now. and we're going to pull off that proton. Those electrons are going to go down, reform the pi bond, reform the benzene ring. Okay, so why do you think it is that this substitution product is more favored over the addition product? Right, because one of them, the substitution product, is aromatic, right? Whereas the addition product is not. Okay, so that's a much more stable product. So if the molecule can, it's going to maintain its aromaticity. Okay, so this process right here is going to be the same for each of the reactions we're going to look at. Okay, really the only difference that we're going to see is, for one, we're going to have to form this electrophile. Okay, we're going to use different electrophiles, so we're going to have a slightly different way to form those. And then, based upon what that electrophile is, this base is going to be different as well, but it's going to do the same thing. Yeah, question?
I was saying, so with this reaction, would any of the addition product form, or would it be all of the substitution product?
Okay, so the question is kind of competition here. I think in this case, there would be no addition product. Okay? It's just so much more stable to go to the aromatic product. Okay? All right, so this is just the energy diagram for this process. Okay, so the first step, of course, is going to be the rate determining step right here, because in this step, we're actually breaking open the benzene ring, right? The intermediate is a resonance stabilized carbocation, but even with all that resonance, it's not as good as an aromatic compound, right? It's no longer aromatic as the intermediate. So the first step is a rate determining step. Here's this resonance stabilized carbocation. In the second fast step, it's just an acid base step where the base comes in, removes the proton that's on the hydrogen where that electrophile is attached. Okay, that's always the one that it removes, because that's the one center right here, sp3, that's getting in the way of allowing this molecule to be aromatic. Right? So you have to remove one of those positions. Okay, so here's just the step. You know, benzene reacts with the electrophile, base pulls off this proton. Okay? If the addition took place instead of the substitution, where do you think that product would be on this graph? Yeah, so if it was actually, addition, it's probably going to be like up here somewhere. And so we'd have E, before I had nucleophile here. Because this is no longer aromatic, it would certainly be above our starting material. The way that they've drawn this as an exothermic reaction, I'm not sure that that's always going to be true, right? The relative energy of this product versus the reactant. But the rest of this is always going to follow in that way. Okay? Okay, so let's kind of just look forward at the reactions that we're going to do. All right? So we're going to have 5 different reactions. Okay? The first one is going to be the halogenation reaction. I'll just write it over here. Okay, and we'll be able to put on chlorine or bromine. Okay, the actual electrophile, they draw it a little bit different in here, but we can think about it as bromine plus or chlorine plus. So bromonium ion or chloronium ion. The reagents we're going to use is Br2 with a catalyst. The catalysts for these are usually iron, like I wrote once before, iron tribromide. If we're doing the chlorination, we do it the same way, but instead of using iron tribromide, we use iron trichloride, okay? Because those we're going to kind of be exchanging. And the products that we're going to get, I'll just put an X here, is just going to put one halogen on the ring. Okay? And substitute for a hydrogen. Okay, the next one we're going to do is going to be called the nitration reaction. Okay, and so this is going to put a nitro group. So we want to remember what the Lewis structure of nitro is too. It's like this. All right, so nitro is kind of unique, or not, I don't know, unique, but it's different in that we have these charges, but it's overall neutral. Okay, the electrophile is going to look like this. So it's called a nitronium ion. And the way we're going to do this is we're going to use nitric acid, and our catalyst is going to be sulfuric acid. So it's a very acidic mix. Okay, the next one we'll do is called a sulfonation. This puts a sulfonic acid on here. The electrophile is going to look like this, with a plus on the sulfur. And the reagents are SO3 and H2SO4. Or you can also draw this. I'll show you when we do it. I think this makes more sense to draw the mechanism with just H2SO4. When you heat it up, it kind of has SO3 in it too. All right, the next two, we have what's called the alkylation reaction and called it an acylation reaction. Okay, these two reactions are named after their discoverers, and so they are both called Friedel-Crafts reactions. So we have the Friedel-Crafts alkylation and the Friedel-Crafts acylation. Okay, the alkylation is going to add an alkyl group, okay, onto the benzene ring. The electrophile is going to be a carbocation, and the reagents are going to be an alkyl halide and another Lewis acid, but on these reactions they use aluminum, usually trichloride, as the catalyst. So it's another Lewis acid. For the acylation reaction, an acyl group, so if we look at this much right here, this is called an acyl group. Okay, and so that's what we're going to add on to this. So we essentially make a ketone in this case. Our reagent is, you can draw it like this, is an acylium ion. We've seen those before. Do you remember where you've seen an acylium ion? Mass spectrometry. Yeah, so that's the ion we get when it cleaves next to the ketone in mass spectrometry. So the reagents we use are, this is called an acyl chloride, and again, aluminum trichloride. Okay, so each of the reactions are going to have two parts. One, the first part is that we need to be able to generate this electrophile. Okay, and the second part, it's going to follow that generic reaction I just showed you. It's going to be the reaction of the electrophile with benzene. Okay? So let's start out with the halogenation. Okay, so we already talked about how we're going to form this product like this. We're going to have this chlorine attached. Okay, so the first part is to generate the electrophile. Okay, and so I'm not going to use that red, but so this is going to be a reaction between the chlorine. So we got to, so that whenever we're doing the electrophile part, benzene's not going to participate in that part. Okay, so we're going to essentially make the very reactive electrophile. So that's going to react with the catalyst. Okay, I already said that the catalyst is a Lewis acid. So in this step, the chlorine is going to act as a Lewis base. Okay, so chlorine has all of these electrons around it. So we can draw the first step with a pair of those electrons reacting with the iron. And if we do that, we're going to get something like this. It's going to be all connected up here. Okay, we got 2 pairs here, we got 3 pairs over here. And we're going to need to put some charges on here. So what are the charges going to be? Plus on the chlorine, minus on the iron. Okay? So this is just kind of a Lewis acid, Lewis base kind of addict. And we can draw, the book shows this as being the reagent. Sometimes in other texts what they also show is having another process that goes to like this. And this essentially makes Cl plus iron tetrachloride with a minus. Okay? But we're going to use this species as the actual electrophile. So let me show you how that works then. So then we're going to take our benzene. It's best to always draw in those H's on the double bond that we're going to show reacting. So it's going to react with this. Minus, plus. And the way this works is this reacts with this chlorine. And these electrons go back over here. Do that. We form our intermediate, just like we saw before. I'm going to draw it here, H, chlorine, with our plus, like this. I'm not going to show it every time, but we know that once we form this carbocation, it can be spread between these 3 positions, right? The positions that are ortho to where the chlorine would be, or para, right? So the final step, we need to have a base to remove that proton. And so what we're going to do here is we're just going to show this other byproduct that came from this part. So we're going to have chlorine, iron, Cl3. This has a minus. And we're just going to use the bond between the iron and the chloride and go like this. Okay, so this chloride is going to come off. It's going to react with H, so it's going to give us hydrochloric acid. Right? We're going to get our product back. and iron trichloride, so we've regenerated our catalyst. Okay, so over here, this is going to give us our product. Plus hydrochloric acid plus iron trichloride. The iron trichloride can go back and react again. Okay, so it's a catalyst. It's used, consumed, but regenerated, right? So it's never totally consumed. All right, everybody follow that? So if we have bromine, it's just the same. We just use bromine and we use iron tribromide. Okay, everything else would be the same. Okay? Nitration is the next reaction. So in this case, we are going to add this nitro group. All right, and this is one that I don't know, I always like this one because of this first part. Okay? And just think about this for a second. Look at our two reagents. Okay? We have nitric acid and we have sulfuric acid. Okay, so what is it about those two compounds? What are they? Yeah, they're super strong acids, right? So we're going to mix these super strong acids. We're going to have this epic battle between these two acids. All right? Because one of them gets to be the acid. And what does the other one have to behave as? A base, right? What upstanding strong acid would ever want to act as a base? Right? This is seriously losing face here. All right? So which one do you think is going to be the acid? Sulfuric, right? Sulfuric acid is a stronger acid. All right? So what we're going to show here is we're going to take sulfuric acid and nitric acid and we're going to do an acid base between these two super strong acids. All right, so like we said, sulfuric acid is the acid. Nitric acid is forced to act as a base. Okay, so when we do this, we get, I'll draw it up here, we get our conjugate base of sulfuric acid plus the conjugate acid of nitric acid, like this. Okay? And then, what do you think can happen? We've just essentially made this water molecule attached to nitric acid. So what happens usually when we convert an OH to a water molecule? Right, it becomes a leaving group and comes off. Exactly right. So then this can come off. And what we oftentimes draw is then as that generates even more plus on that nitrogen, the oxygen with the minus charge can donate its electrons down. All right, and let's come back this way. So then what we get is water plus this nitronium ion. Okay, this is nitronium ion. And that is the electrophile. Okay, now we can just do our reaction with benzene. Okay, so it reacts with this nitronium ion just like we've seen before, right? So we have this reaction here. Of course, that nitrogen already has 8 electrons around it, so it has to give up some electrons to one of these oxygens. Okay, if we put it here, notice here's the O minus that I just generated. We still have the plus on the nitrogen, and we have the plus on the carbon. Okay, so just like before, we've generated this resonance stabilized carbocation. Okay, so what do we have to do now to get to the product? Right, we have to have a base, we have to just remove a proton, right? And so our base now is usually going to come from that reaction to generate the electrophile. So we're just going to use, not that it's a very strong base, but we're going to use this bisulfate, the conjugate base of sulfuric acid, because sulfuric acid is acting as our catalyst. We want to regenerate the catalyst now. So these electrons come over, they pull off the proton that's attached to the same carbon as this nitro group. Those electrons can go down to reform the benzene ring. Okay, so then this forms like this. We get a nitro group plus sulfuric acid. Sulfuric acid can go back up and react, go up and beat up on another nitric acid molecule. Okay? So you notice the trend. They're all following the same procedure here. All right? Oh, the water just went in there somewhere. It's right here, right? Sulfuric acid, even those concentrated acids have their own, have water in them. So it's just going to go in there. One more. Sulfuric acid, sulfonation. Yeah, question? All right, so sulfonation reaction, we add this sulfonic acid. So we could draw it like this, OH. Okay, I'm going to show you 2 ways to form this electrophile. Okay, because I like the first way better, but then I'm going to and this one is the reaction of 2 sulfuric acid molecules with each other. So if we compare the last one, maybe sulfuric and nitric acid maybe is a battle between 2 brothers or something, or 2 close friends, right? Both strong acids. This one, we have 2 sulfuric acids, so it's actually like identical twins fighting it out to see who has to act as an acid or a base. All right, so one of them has to be the base. So I'm going to draw this one on the right as the base. All right, so this is going to then generate the bisulfate. There's the conjugate base. And then we have a sulfuric acid that's been protonated with a plus. So like we did before, we've now added this water molecule on the side, and it acts as a leaving group. So this comes off, gives us a water and this species right here, which is our electrophile. Now let's just put a water over here. Okay, the other way to make this, which is how the book shows us, is This is sulfur trioxide. So this mixture of either heating up sulfuric acid or sulfuric acid with sulfur trioxide is oftentimes called a fuming sulfuric acid. So this is probably what they could have used almost instead of HF in Breaking Bad, if you ever watched that, and then they like chew up these bodies and stuff, you know. So in this case, you can just take one of these double bonds in sulfur trioxide, and it just protonates that one. It goes straight to this compound here. Okay? Because we move this bond up, put an OH, leaves a plus behind on the sulfur. All right, so then here's our electrophile. We just do the same thing as before. You guys know all of this stuff already now. Right, here's our first step. There's a plus already on here, so we don't have to push a bond up. Remember, sulfur being in this third row of the periodic table can make more bonds because it can use d electrons. So then we have this. With this, our resonance stabilized carbocation, just like before, and then we can just use, again, the conjugate base of sulfuric acid. I'm going to run out of space here. Here it is. It can act as the base, removes the proton that's attached at the same point as the electrophile to generate our product and regenerate the sulfuric acid that was acting as our catalyst. All right? Okay, so we got two more of these. We'll talk about them on Monday, but again, they're just going to follow the same process. All right, so have a good weekend. Make sure you get all those the assignments done before class on Monday, right?